You can group them by color, which probably would not happen with minerals, because too many minerals have the same color, and too many of the same minerals can have different colors. Okay, so classification is the system. And what we're going to look at today are silicates, so this would be a chemical classification. And the group we're talking about is going to be a lot to classify because there's differences within the group. You know what this is?
Table of Mendeleev.
Say it again.
Mendeleev table.
Periodic table of the elements.
Periodic table, okay. So what does it show us? It's all the elements that are in everything, the bricks that build the earth. And when the earth was first formed, they were all there, all mixed up, some more common than others. And you can find these by themselves, or you can find them in combinations, because they join together and bond. So how many minerals are possible, depending on other chemistries possible, and it's unlimited. And we're getting new ones all the time, because man is creating a lot of them. So, is what man creates a mineral?
No.
No. Because by the definition, it's inorganic and it's natural, so we can't include those things that man makes. What do we learn from this? Well, first of all, it starts, and this is just a slight review of chemistry, because we're going to be talking about silicates, and something about them has to do with chemistry. You start with the lightest ones at the top, and as you go down, everything gets heavier. And what happens is when you line them up like this, those in the same vertical column have very similar properties, because the number of electrons that occur in them are the same. And I have copies of this for you, because as you can see, this is not complete. And these are copies that I give my students. First of all, thank you. Took a while. All right, the periodic table. I think I have to tap this for everything. All right, we're tapping and we get, all right. So, they display symbols because you want to write all these names out when they bond and get them together in combinations. It's found on the earth and other places, but what we're talking about was found on the crust, because that's where the definition of mineral comes. All right, it has the atomic weight of each element, and that weight comes from three particles, the protons, the neutrons, the electrons. And remember, the electrons are so small, they're like 1/2000th of what a neutron and electron and proton are, and you know they're small to begin with. So in order to get the weight of an atom, you have to just add the protons and neutrons together. Okay, the electrons negligible. All right, atomic weight. And of course, since they get heavier as you go down, that should be included. I'm tapping, guys. Oh, I'm sorry. Tapped the wrong place. All right. There is a line on the periodic table that goes down over here. We saw before a little bit darker line, and it separates those that are metal from those that are non-metal, and they bond opposite metals to non-metals most of the time. And that number that is given to each of these is based on the number of protons. So every element is different, and you can recognize it if you can count those protons and say they're awfully small. Okay? So that's it for the periodic table. See a quick review. All right, so this is the system that we have on the back of this card. So you can get your international atomic weights if you need them. I doubt it. What you see here, if you just notice it, is you have all the electrons on the right, and in here, in the middle, you have the number of protons, neutrons, electrons to each element. And what do you notice? As you go down here, the protons don't have to equal the neutrons, right? 6 and 6, but here's 7 and 7, and then there's 9 and 10, and 10 and 10. So they don't have to be the same. However, the number of protons equal the number of electrons, 5 and 5, 6 and 6. Do you know why they have to equal the same?
If they don't, it's an ion.
To stabilize the...
Speak up.
To stabilize the nucleus, to make it stable.
Right, it's stable because you have positive equals negative. The electrons are negative, the protons are positive, and the neutrons are neutral. So as long as you have an equal amount of electricity, positive and negative, it's going to be a stable piece. Now, they don't always stay stable because they lose electrons, and if they lose electrons, that's losing a negative particle. That means this becomes positive. See?
Ergo, it's an
See,
ion.
so you got positives and negatives, and if you lose the little guys, the negatives, it becomes positive because that's stronger. So that's why things join together. Okay. All right. So this is a good chart, and you have it a little bit of it back here. Do they have the electrons? No.
Now, this chart is
I got it.
different.
Yeah.
Definitely.
Doc, you know this chart's as old as I am.
Okay. So we're just doing. Is it?
May
okay.
66.
You're
And
no
if the
longer.
20th is the date, that's my birthday too. This is 57 years old.
You're not supposed to read it so quick. All right. Now, this is a small chemical review that you should know. The smallest particle of each element is the atom. It has 3 particles, and they just differ by the number of protons on the periodic table. Okay. Now, the minerals we look at can be either an element, okay, or it could be a combination of elements, and those elements have to bond, okay, and that means if you take 2 elements with their own properties and join them, you're going to get new properties. It's going to be different. For instance, you take iron and sulfur, and iron is magnetic and sulfur is yellow bright, and you get them together and you get pyrite. And pyrite it's not magnetic and it's not yellow. It's got its own color. So the properties change. Take a look at water. Hydrogen is the lightest element. It flies up, and water has oxygen, and oxygen is also an enhancer of fire. You put it together, all right, and it's totally different. It's wet. Okay, you got a gas and a gas, put it together, and you have a liquid. And water is totally different. Salt, the same thing. You have a dangerous gas in chlorine, a dangerous metal in sodium, and you put sodium and chlorine together, and it's neutral for us. We use salt in our food, and yet those dangerous elements put together, their properties change. So that's just a quick review of chemistry. All right, was it quick enough? All right.
Too quick for me.
Too quick, yeah. All right. We're working. Little diagram of an atom, okay? And now elements can combine, and that's where all our minerals come from. The elements and the elements in combination. Okay, when they join chemically, they use energy to do that. They change their properties. They're no longer counted as atoms. They're called compounds, and they're counted by molecules instead of atoms, because they're groups that are stuck together. Okay, so we're going to start getting into the minerals themselves. That was just a quick review of chemistry. All right, so what are we looking at? We're looking through minerals. Any mineral that you make thin enough, you can see through. They're called thin sections. That's what we call them. And things that you don't think you could see through, you can. All right, make it thin enough, and light will pass through. So, what do you think this is? It's cubic. You see it? See the bricks?
Pyrite?
Okay, could be, right? Because pyrite has crystals that are cubic, right? Anything else it could be?
Halite.
Say again?
Halite.
Halite. Yeah, that's what it is. It's halite. It's salt. Okay? Now, most of the time, if you grow salt, you'll get something that looks like cubes. All right? You could take it by just dissolving it in water and then let the water evaporate and crystals will form and you'll get cubes like this. But seeing through them, okay? Why are they different colors? Just depends on the light passing through it. Okay? Depends on how thick it is and what angle the light is, and voila, they change colors. You can't depend on color. You have to depend on other types of properties. And right now, all we see is these grains grew in squares, in cubes. All right, so that's the natural growth of salt. And if we put the salt together, the sodium and chlorine, this is what we get, a pattern. That arrangement, the structural arrangement of any mineral is its structure, is its network, and that is usually very orderly, and it creates a field, a magnetic field, and it also gives this a property and the way it grows. Given enough room, that will continue to grow, and you will see in its growth the pattern and the structure of the way the atoms form. When you look at a crystal, you're looking at the way the atoms attach to one another. All right, and this is the smallest bunch of molecules put together of salt, and it is cubes. And as it grows bigger, we start to see it. Can't see it too small. We're learning about this because of a process known as X-ray diffraction. Okay, so that's a course in college. Now salt cubes, you can see when you look at the picture on the right, you can see the cubes when they're small, that's a microscopic picture, and you can see what the cubes look like in the model to the left. If you were to look at inside of it, come on guys. All right, if you look inside of it, you would see that same structural pattern. All right, so that's normal for every mineral. It's going to have structure. It's going to be a network of orderly arrangement of atoms. Okay, does it happen all the time? No, there are exceptions to every rule. You know, we make the rules and Mother Nature knows how to break them. So we're just giving you the general rules. But like I said, there's exceptions. We'll get to the exception in a couple of minutes. All right, so now we're going to talk about minerals. Okay, our definition, okay, is they are inorganic, which means not from a living thing. They're elements or compounds. They're formed in and on the crust of the earth, and they're natural. Okay, so there are exceptions to this too. All right. Remember, you can call something a mineral, but you can also call it a stone or a rock. Okay, you know the difference? Stones and rocks are pretty much the same, but a mineral has this same internal arrangement, but stones don't have to. Stones can be made of different minerals put together, right? And stones, you don't always see the properties that. Why those three pictures? Recognize them?
They're all quartz.
They're all quartz?
They're all quartz, right? And you can see quartz has a variety of colors. So color is not a way to identify it, right there. Okay, so what are the most common elements? Let's take a look. First, in the air, it would be nitrogen and then oxygen, right? They're pretty common. And then if we talk about in the ocean, I'm just playing with the computer here. Okay, what's the most common in the ocean?
Water.
Water is not an element.
Salt.
Hydrogen.
Hydrogen, yeah. Okay, here we go. Got that one right. Yay! All right, and what about in the crust of the earth? What's the most common
Oxygen.
element?
Oxygen?
Oxygen. And then comes silicon, number 2. All right, and basically anything else added to that is a silicate. So we finally got to where silicates are. So silicons are based on the most common elements in the crust of the earth, and therefore they're going to make the most common minerals. That makes sense? Good. All right, so we take a look at most common of everything on the crust of the earth. Oxygen is number 1, silicon number 2, then comes aluminum. So the next most common family of minerals is aluminum silicates, and then you could add other things to it, the iron, the calcium, sodium, potassium, magnesium, and then all the rest of those elements can create things. There are compounds that are made of 10 different elements. Okay, if you look into some of them, like the boleite, which is something I was on a treasure hunt for down in the Baja, Mexico. Boleites are lead and all copper and iron combinations, and they're not all the same. But they all seem to produce the same metallic blue cubes. And the only ones in nature. That's why I went after them. Did I find some? Yes. Found a few. All right. Okay, so here's what we're starting with. We're starting with oxygen and silicon, and they're going to end up being the most common. Why? Because as these things start to join together, what's most likely to be left? The oxygen and silicon. Because after the smaller ones get attached, that's what's in the soup. All right, and what do you get with silicon, oxygen? Quartz. All right, or what you can call it silica if you like. All right, so here we go. All right, so we have to think about properties, okay? The property by definition is defined as what belongs to you, your property. So every mineral has qualities and characteristics that belong to it. Boy, that's an awful lot to know if you have 5,600 minerals, right? A lot of properties to remember. But that's why you take them a little at a time, okay? So what we should do is study maybe a family. Like we're doing today, we're studying a little bit of the silicates, but there's a whole, the silicates, I'm giving you a lot to swallow here because silicates are a big family. Okay, so now every mineral has properties to identify it, and that's what we like to do, identify it. The physical properties may be used more easily in fieldwork. And here's the list. Okay, why in fieldwork? Because there are a lot of properties that you need help with. In a laboratory, it's much better. You need a microscope. Okay, sometimes the grains are so small, you need help. Or you need to test it, and you don't always have the equipment with you. So these are honed for being used while you're out in the field. Okay, there's a lot of properties. Let's go. All right, now we're talking about physical and chemical. Look at this list, wow. It's big. You got luster, cleavage, fracture, hardness, fluorescence, magnetism. Yes, I should put fluorescence back in the lab, because who wants to carry a lamp around with you? Magnetism, acid test, streak test, habit, crystal habit, color, and behavior in light. Okay, all of these things you can do in the field. Acid test, a lot of people like to keep a little bottle of acid on them, and then for the magnetism, you don't want to carry a magnet, you carry something made of iron, and if it attaches to the rock, you know that it's magnetic. And I have to tell you, everything is magnetic somewhat. It's like saying everything really dissolves in water. It does. Only some things dissolve so little, they're called insoluble. But they do. Everything does dissolve in water. And like magnetism, everything has a certain amount of magnetism to it. But sometimes it's so infinitesimally small, you call it non-magnetic. See, so you got to know your definitions before you begin. I did my thesis work on magnetic minerals. I passed them through a magnetic field and tried to classify sands from different places. And I found out some interesting things when I did it. I discovered some things that they wanted me to do more work on, but it just wasn't my bag. I wanted to go out there and look. I wanted to find more minerals. I didn't want to be in a laboratory, so I kept going. We're going to go into the properties, each one, just to see how they expand as well. All right, so we're looking at, for the silicates, the way silicon and oxygen join. Okay, those two are the most common. They join together because they're the most common, and they make a durable combination called silica, all right, which is the mineral quartz. Most sand is common quartz. Most silicates are built with something called a tetrahedron. Tetra means four. All right, this is a tetrahedron. Picture this in 3 dimensions. See the little red pyramid? It has 4 sides. I can put my fingers on it this way. 1 side, 2 side, 3 side, 4 side. It's a pyramid, 2-sided pyramid, tetrahedron. It's hard to see that just from the picture. That's why I wanted you to handle it and see it. The tetrahedron is the unit building the silicate minerals. And you can see in this picture that it's attached to more of them. Okay, so it has 4 oxygen atoms, 1 silicon, which is in the middle. So this pyramid has 4 oxygen on the corners and the silicon in the middle. Okay, and it does this as a single unit. There's 2 pictures here. One showing you the pyramid. Is that on the left?
All right.
Right. I'm sorry. It's on the right. Okay, it's on the right. You're right. Okay. And on the other side just shows you how the atoms are attached. They're attached from center to center. That's where the gravitation pulls. So that's where you get the pyramid picture. The center of gravity is for every atom. And this is a silica or a tetrahedron. Okay. Now, what happens in the silicate families is that these tetrahedrons join in different ways. As you can see in the first picture, the tetrahedron is by itself. This is, for example, a mineral called olivine. And I'm going to give you so that you don't have to take notes today. I'm going to give you a picture of this, and it has 2 sides. A side with that picture showing the way the silicon tetrahedrons connect in 1, 2, 3, 4, 5 groups, and then I have several groups here, slightly different, a description of them and what they're called. So notice that this group here is for olivine. The group below it with single chain is the pyroxene group. The double chain is the amphibole group. The sheets are silicates are the mica group, or this also goes for clays, because what is clay but just broken down micas, and then framework silicates are the quartz and the feldspar group. Quartz and feldspar are the most common, and that's this framework. Look at the way they're put together. It's kind of like cages, and the cages allow for liquids to pass through, but they do capture larger elements so that they're great for filtration. So this group is probably going to include the zeolites. All right, so we're looking at the way tetrahedrons connect and form different groups. All right, the groups, I gave you an example of each of them. Is it on the paper? You got that group name there? Okay, so if we go to the next slide, oh, I missed that. All right, here's an example of olivine. Okay, all of the grains are singular and they don't attach to one another. This is the pyroxene group, the next one. Going down with a single chain, and you have the double chain in the amphibole group. I don't know if this is a great picture, but the pyroxene was good. What I noticed about the difference in pyroxene and amphiboles, they're both dark, they're both heavy minerals, and the pyroxene group, the cleavage is usually like this, and with amphibole, the cleavage is like this. So it's easy to tell if you identify cleavage, and we're going to get to cleavage, right? All right. So next group was the mica group, right? And this is a great picture of mica, but you can see on the edge, on the right edge, that it's layered. And these are sheets. You know, mica, it just peels off. As a matter of fact, if you take a muscovite mica sheet and peel it, it'll be so thin you can see right through it like a window. All right? In fact, I think there are
Which, by the way,
societies that do use
it
it.
was used in like old basement burners and stuff as the glass.
Yeah.
Yeah, from
Yes.
Yeah.
with the stoves. Yeah.
Okay.
Yeah.
I'm a little hard of hearing. You're saying it's used as windows and stoves.
Uh-huh.
Yeah.
Okay.
Yeah. Grew up with
You're allowed.
Yeah.
All right. Okay, so, and the last group were the feldspars and groups. This is an interesting crystal of feldspar. Okay, here's where we're going. Okay, the classification. Okay, you will see when you look up a mineral that if it happens to be a silicate, it's going to be described as either a nesosilicate, a sorosilicate, a cyclosilicate, an inosilicate, phyllosilicate, and tectosilicate. Well, what do those mean? Those are the names of the different groups. So it's not identified by the mineral, but by this name that they use. So you can just put different minerals in it. Now, what I did here, if you look under the second grouping, the sorosilicates, you can see two names here, hemimorphite, smithsonite. And it's again a double tetrahedron groups, okay? And the rest, I'll go on. If I go all the way to the bottom, you'll see that the tectosilicates are the zeolite family. Those minerals that are found in lavas. Okay, they're good filtration, you know, the things that you're used to seeing as so many names flying around. And not prehnite, but those things that occur with prehnite, like eulandite and the radiating one, pectolite, all of those are the zeolites. You can have a talk just on the zeolites if you want, because there's so many of them. They're beautiful, and we destroy them. Okay, when we crush them up, and then you look at a rock, and you see all these colors, and you see, so what am I looking at? Each one of these colors, they could be the same mineral, just in a different color. It could have been deposited at a different time. And you have to ask yourself, well, what am I looking at? Well, you have to look at them. Are they crystals interlocked, or are they separate grains? And are they round, or are they angular like a jigsaw puzzle? If they're angular like a jigsaw puzzle, they're igneous. If they're rounded, it's sedimentary. And if they're aligned, so your eye sees an orientation, that's when it's metamorphic. So you're looking at this, and it may be different minerals. The quartz could be the clear ones, the gray ones, and the white ones, and the pink ones could be your feldspars, and the black ones are the associated minerals like micas and tourmalites. Okay, all right, so you look at this, what property you're looking at?
Pyrite.
Crystal shape.
Crystal.
Okay, and if we look at a whole bunch of them, they all have different crystal shapes. Okay, This, as you can see on the bottom, they give you the answers to what each of these is, but you see the shapes are different, so that's important. Okay. If we're looking at lusters, the luster is the way the light bounces off the surface. How many are there? There's a lot of different lusters. You have glassy luster, sometimes referred to as vitreous. You have waxy luster. You have to think about the way wax reflects light. Pearly lusters, metallic lusters, resinous lusters, adamantine lusters, silky, and dull. There's a lot of lusters you have to be familiar with. So that's what you do in a mineral course. You look at specimens and identify those lusters. You have to have it in here. You have to have seen it to be able to recognize it. How many of you know what resinous luster looks like? Why is it called resin? Those of you who play an instrument like a violin or viola have to take rosin and dry your bow up on it. The luster from resin comes from that rosin. One particular mineral I have here called sphalerite has a very unique resinous luster, okay? And that's what helps you to identify sphalerite when you see it. And sphalerite's pretty common, it's all over the place, okay? Even the quarry down here on Cherry Valley Road has the mineral sphalerite in it. Okay, so you can see, why else would you need to, let's say, know a pearly luster? Well, sometimes when a rock breaks, it breaks into cleavage. Cleavages have a pearly luster. So that helps you to tell the difference between what's a crystal face and what's a cleavage face. Because they're all the same. They're flat, they're shiny, and they're different. One is produced by growth, and one is produced by the way something broke. Weak planes in the atomic structure make it two flat sides. Okay, it's a dimension that creates cleavage, but it's the atomic structure that creates the facets of a crystal. So it's important to know these lusters. And maybe we'll have a short talk just on lusters so that you can see them and be able to identify them when you do come across them. And you have to remember, they could be very tiny. And to you, sometimes with the naked eye, you see just a sparkle. But you have to get that hand lens there and get to see what that luster really looks like. So you see what you have to educate yourself to do to identify minerals, okay? And luster is pretty important because that you use in the field when you're out there. You don't have to bring it back to a laboratory. You can be right there. Use your eyes and a magnifier. Okay, so I'm just giving you some reasons why you need to know your lusters. Okay, one, it helps to tell the difference between a crystal face and a cleavage face. And two, they can identify a compound right away, like resinous. And you may have seen silky. There's a lot of common materials that do have a silky luster besides other lusters. I mean, one mineral can have several lusters, okay? Like gypsum. Gypsum can look like glass, and it can also look like silk. There's a glassy gypsum, there's a selenite gypsum, that's glassy, and you have the satin spar variety, which has these lines on it that look like silk. Okay, so just depends on other things in the environment when it crystallizes. Another test you're going to use is the street test. The street test uses a little plate that you can keep in your pocket. It's small, it's rough, it's porcelain, and it's hard. It's got a hardness of about 5 or 6. And that means that right away you can rub it on the plate and find out what the color of the powder looks like, because the color of the powder doesn't always look the same as the mineral. Sometimes it's different. You get a red luster, you know you have hematite. It's a unique kind of test to tell right away. And there are a lot of, there are some hematites that, or limonites similar to it, that have a yellow luster, and yellow powder, and the street test is one of those things. They recently, last time I was ordering materials for the class, they came out with black street plates. And of course, if the mineral is harder than the street plate, it's not going to powder at all. So many minerals have no powder to identify because they're too hard. So only the softer minerals with a hardness less than 5 are gonna come out on this street plate. So,
I have an interesting little
Excuse me.
story to say about street.
go.
We were at a quarry with serpentine, and piperlite is bright green. It's a serpentine. I found a little piece that was perfectly green. I put it in my back pocket. It stayed in my back pocket for of my jeans for 2 days. I pulled it out, it was white. Because being in my back pocket, it was the chalk, it was the street, basically, that got rubbed off the green.
I thought it was body heat.
Yeah, I was gonna say, it just
No.
because of sweat.
That was a
No.
warm powder. Mike.
Well, no, that was the powder.
Okay.
So if you
It's
wash
different.
that off and then it turns green.
Anybody know what the powder of
If I
pyrite is?
scrape it, I'd have to scrape it off.
Pyrite is gold. What powder does it make?
Black?
It's black.
No,
It's black. It helps you identify gold from pyrite. The easiest test for telling whether you have gold is its malleability. Pyrite, if you take like a knife blade, you carry a knife on you, I'm sorry, it's a weapon, and you press down on the pyrite, it will shatter. But if it's gold, it'll flatten out. So it's one of the quickest tests. That's why in the old West movies, they took the coin to put in their teeth, because they were hungry.
For gold.
So that's the street. Then you can have a little bottle of acid, do the acid test. And of course, you can have a lot of reactions. You can have smells come off. You can have color changes with the acid. And of course, the bubbling, which helps you identify carbonates. Okay, that's one of these things. Okay, we're taking a look at this. All right, what test does this demonstrate by just looking at it?
that's,
I mentioned it already.
Luster?
Say it again?
Luster?
No lusters, no light giving off.
Cleavage?
Cleavage. Cleavage is a straight side that breaks because of a dimension between atoms where there's a weakness. And it always appears in pairs. So you can see the pairs there, okay? Nothing else to study, right? It starts with the top one. A mineral can have a flat cleavage. Every time it breaks, it's flat, like mica, right? And that would be called basal cleavage.
So
The base just peels off, right? The next one is two planes, just two, like feldspar. And then beneath that, another one with two planes, okay? Then you have the one with three planes, the fourth one down. The fifth one down is also three planes. The sixth one down is, am I counting right? Yeah, sixth one down is 4 planes.
big calcite, one of those.
And then, hold on, and then the last one down here is, how many planes? I forget. 8. See, I'm getting old. I don't recognize how many planes are there. Probably in the story below. All right, so, question. Which one of these would be called prismatic cleavage? Yes?
I was counting down.
How many?
Third down.
Well, actually, they're lettered. Actually, it's A, B.
No, we can't see that from here, what are you crazy?
It's too small. All right, which one down?
C.
C.
C?
Prismatic. Yes. So is B. A trick question. B and C are both prismatic cleavage. Okay, what's a prism? How many of you know what a prism is? You know? All right. For those of you who don't. A crystal grows, do we have a board? Nah, all right. A crystal grows with coming up opposite gravity. All the atoms fall down, and then it appears like it's growing anti-gravity, right? Because it's growing up. And then when it gets to the top, you see a pyramid at the top. Okay, so the top is the pyramid of the crystal, but the sides going down are the prisms. Okay, so prismatic cleavage means that the sides opposite themselves, this way, or at an angle. And you can see the first one here is at right angles, and the second one is with acute angles and obtuse. So they are, you know what those words mean, right? They're mathematical angles, and they're both prismatic cleavage. The third one down would be cubic. The fourth one down, cubic. You have rhombic cleavage. They look at rhombs. then you have octahedral cleavage, and then, what's this one?
Hexa?
Say it again?
Hexa?
Dodecahedron.
Hexa.
No,
Because that one's
come on, you.
Octa?
octa.
Octa.
Octagon?
I don't hear it.
No,
Dodecahedron.
That's it,
octagonal.
dodecahedron.
What is it?
Well, you're a good learner. Alright.
I've
Dodecahedron.
been doing this a while.
This is a dodecahedron.
Did it have to be a pentagram or, yeah, pentagram for, dodecahedron, 5 sides?
If you count those, remember, you are looking at one half of it. Count the number of sides facing 6,
Garnet's a good example.
right? That means there's 6 you don't see.
Yeah, here.
So you're
So
saying
there's
it's
12
12?
sides.
So you're saying it's 12
You
sides?
got one?
I got one.
Alright.
I carry it around.
Okay.
Professor, you're losing
it's
your
a nice
hearing,
one.
some of us
Nice one.
can't see.
It's 10.
I have beauties in nature. Yeah. Here's a nice one. I don't know if this one's nice. Oh, yes, this is nicer than yours.
Oh, yeah,
You see the extra faces?
yeah.
There were other faces imposed on it. By the way, there's a word that's used in crystallography called coin. When you have a cube and it's missing all the corners, those are how many corners does a cube have?
4.
4.
8.
8.
Yeah.
8?
Okay. If you take a corner off at every if you take the corner off of a cube, what shape was it that removed it?
How does that happen?
Ooh, that's good.
There's 4 on the top and 4 on the bottom, and they're all at different angles. What shape was that? If I extend those out, what do you get?
Octahedron.
You get
12 sides.
an octahedron,
Tetra.
right? When you see a cube with corners missing, that's another crystal imposed on top of it. That's a group. And
I'm still trying to figure this out.
This is one of them. This is a
Somebody
A
can
garnet,
die.
a
She's gonna break the die
dodecahedron
so she can count
with
the sides
other
of the square.
faces
She's really
imposed
upset
on
about
it. It's a
Just
amazing
hand her
specimen. It's not polished, it's natural. That's what makes it so special. Okay. Well, you know something, a lot of things happen to
I just
crystals.
used to hand her a
Take a
die.
look, it's just a garnet, and it's an
Ooh,
almond
it's
from
heavy.
Alaska. Alaska's got a lot of them. And a friend of mine was taking stuff out of Alaska, sheets of schist, which had garnets in it, and he was blasting it with a water spray, and all the mica was coming off, and the garnets were standing up out of the, because garnets are so much harder than mica. He was able to get them to stand up on the schist. It was amazing pieces that he was creating.
5.
They were selling them in Manhattan for like $500-$600 each. Okay, so, is cleavage necessary? Absolutely. And remember this, cleavage is always seen with a pearly muscle. That's how you identify cleavage. And cleavage always exists in pairs, okay, and they're opposite one another. And sometimes you don't always see the whole face, sometimes it's just a little piece opposite, okay? If you don't see it, is it a crystal face? Not necessarily. You have to look for that other face somewhere on that other side to see whether it's crystal or cleavage. It's been a quantity for students ever since the study of mineralogy began.
Doc, for
Yes.
prismatic, you might want to tell the class that it's, think back to the Pink Floyd album cover. Yeah, the prism on the Pink Floyd album
I don't
cover.
have to tell you now. Thank you.
Some of us are too young for that.
Okay, so this is another thing, another aspect of mineralogy you could
Some of
study. It's
us
just
are
cleavage.
older than us.
Being able to take a specimen and identifying the cleavage that's available or observable. Okay? So, we got luster, we've got cleavage. Of course, this all pertains to silicates because you need to know these things in order to identify the silicate groups or what you have. Okay. See how much there is to know? It blows my mind. Okay. What's important in studying mineralogy is hardness. The reason is that you can identify whether something's worth picking up or not. You want to pick up something that's harder than normal, because those are the gemstones. and they're rare. Okay? And hardness, as you can see, is tested with stuff you have on you. Okay? You can either scratch it with your fingernail, and you know it's considered soft. You can scratch it with a copper penny, then it's medium, or you can use a steel knife. A steel knife would mean if you can't scratch it, it's hard. If you can scratch it, it's medium. So just those three tools, your fingernail, which you don't want to ruin them anyway, you could use something else, a penny. A steel knife, and sometimes glass is useful because if you want to tell if it's harder than glass, it's over 7. And you can see that there are a lot of minerals that characteristically take a hardness from it. Oops, I'm sorry, goofed up, too fast. All right, now this is what we call a hardness scale. It's something that is useful. I memorized it because I put a sentence with this. T, G, C, F, A, F, Q, T, C, D. You can make up your own sentence. I have a weird one, so I remember it because it's weird. Two girls can find all other queens tentatively collecting diamonds. It's something I remember. You can make up your own sentence. Here's the point of information that's important about hardness. You can have a scale that goes from 1 to 10, but they're not really the same space between them. The space between talc and gypsum is 1 unit, but when we go to gypsum to calcite, which is the level 3, it's actually 9 times greater, the hardness. So this scale, the absolute hardness scale, is very curved. Okay, it goes when you get down here, a corundum, which is your sapphire family, is 400. Okay, but then when you go to diamonds, it's 1500. Look at the difference between a sapphire and a diamond. A diamond should be able to cut sapphires real easy, right? So just remember that with the hardness scale, from 1 to 2, they're both pretty soft. You can scratch both of them with, and this is what's called a scratch test, right? It's important because it identifies all your gemstones. Any questions? Right? And of course, you need more than your fingernail. You need something on you that's harder than 5, all right? Something made of iron, a nail, a metal nail, or a knife blade, which most people use. That's important. Then you know something's worth picking up. You know, that's a big question for beginners. That rock's interesting looking. Should I pick it up or not? Right? And
What's
the ones
the
that are
hardness?
harder
What's the
are
hardness of
easier
iron?
and nicer to polish. Yes,
What's the hardness of iron?
about 5. Yes.
Is there anything in between 9 and 10 as hardness? Any mineral between 9 and 10? Let's say, because it's
Most likely. Most likely. But you should just know it's hard. That's the important part. It's hard. It means it's rare and it's got a hardness that nothing's up there except the rare stuff.
Because the difference between
I'm sure
9 and 10
there's a lot of
is so
family
huge.
in the corundum that have a variety of hardnesses that go up and down. It's not just a definite level. Hardness, it varies depending on the impurities. You can't have, you're going to have things harder than 9 and softer than 9 and still in the same family. It's the way nature is, okay?
Well, there's, like Serge was trying to point out, there's such a big difference between, the 9 and the 10. So there's got to be.
That's what I was
minerals.
pointing out.
Yeah.
I know I've seen things that they say are 9.5, I just can't think of what the minerals are.
I can't remember either.
Yeah, they're, relatively,
5,600 of them.
yeah, they're relatively rare,
Okay.
but you know the name of it, but I just can't remember what they are.
Okay, I'll hold you to that.
Are there different types of hardness? For instance, like names like Smith hardness and a different type of hardness.
No, they go by number.
Okay, that's
Makes it
it.
easy for us. Or, more importantly, just hard, medium, and soft. Group it that way, you're fine. Then you know which ones to keep. It helps you tell the difference between an aquamarine that's clear and a quartz crystal. Okay, key point. A mineral is naturally occurring inorganic solid with a definite chemical composition and uniform atomic structural elements. So this added a little more to it. Minerals can be identified on the basis of those characteristics, physical properties. By the book. Question. Which of the following cannot be classified as a mineral?
Glass.
Say it again?
Glass.
Glass has no structure, all right? It's amorphous. The atoms don't attach, they're just frozen in space. All right, take a look at these pictures. Examine the following images of the mineral halite and identify how many cleavage planes are present. Cleavage planes. How many?
6.
Incorrect.
3.
3. 1, 2, 3. A plane is a direction, okay? So that's a cubic. Right? Cubic has 3 planes of cleavage, maybe 6 sides, okay? You're not counting sides, because 2 sides are the same.
That's what's so
Now there are
puzzling to me.
those properties which you wait till you get to the laboratory for, okay? I just went through a big list of them, and I just enumerated on a couple of them to show you how much you have ahead of you, okay?